Alright, what's up, guys? We're back at it again with exam 3 from 2018. Um, there was a little bit of a problem at Heldenfeld's last week. For all that know, there was a gas leak, so the exam got canceled, and they postponed it to this week, the week that I'm uploading this video. Um, so yeah, we have more time to study. So I thought I'd do another exam. So let's do it. Okay, so the first question, I already did that in the last video, the derived expressions. So we'll just skip over that one this time around. Yeah, okay. So we have question 2. Okay, so a small object of mass m moves along a horizontal track. Its distance from some point P is a function of theta, the angular position, and is given by 2h minus h cosine theta, as shown below. The object has an angular acceleration about p given by c1t, where c1 is a known constant. Find the object's acceleration as a function of time if it is rest at time equals 0 at the position theta equals 0. Okay, yeah, this isn't too bad. Let's see. Sorry. Okay. No. Okay, cool. Here we go. Let's see. So we know that r is equal to 2h minus h cosine theta. Okay. So that means dr dt is going to actually move this over a little bit. Oh, okay. It's doing what it did last time. Okay, so r equals 2h minus h cosine of theta. And then dr dt is going to be the derivative of this, obviously. But what we want to do is, since this is in terms of theta and h is a constant, we need to take a derivative with respect to theta. So the way to do that is by splitting it up like so, taking a derivative like this. Because that way, these cancel out. These two thetas up here cancel out. And that way it's similar to taking dr dt. Because this is r right here, and then this would be dr d theta times d theta dt, and the d thetas would cancel out, leaving the dt. So that's going to give us a 0, and then, okay, so that's going to be h sine of theta. Okay, cool. That should be right. Yeah, because cosine's negative. Okay. And the dr dt, oh, well, actually, sorry, it's going to be omega h sine of theta, because that's what dr d theta dt is. Okay, and then we have that d theta, the second derivative, dt squared, is just dt of this, which we would use product rule on. So that would give us d omega dt h sine theta plus omega h, and then kind of the same thing here, d theta dt d theta of sine. And so that's going to end up giving us that's alpha, so we can write alpha h sine theta plus omega squared h, because that's omega cosine theta. That should be right. If it's not, I can re-upload this video, I guess. Okay, so that's good. That's a good thing to start off with. So we want to find the object's angular momentum. So write that here, r cross p, which also equals mr v theta k in the k direction, which also equals mr squared omega in the k direction. Okay, angular momentum about the point P and the object's acceleration as a function of time. if it is at rest at time equals 0, at position theta equals 0. Okay, cool. So, let's see here. And we know that the angular acceleration, so alpha equals c1t. So we know that alpha equals c1t, right, angular acceleration. And so that would mean omega equals 1/2 c1t squared plus some constant, theta, omega naught, but that's 0 because we're starting from rest. Okay, see, starting at rest. Yeah, okay, so omega naught would be 0. Okay, cool. So now we can kind of just start plugging this stuff in. So angular momentum is just going to be mass, which we know, times the radius, which we also know. So 2h minus h cosine theta squared, right, times omega, which is this. So 1/2 c1t squared. Right? Okay, cool. That should be correct for angular momentum. And if we draw a free body diagram, this thing is moving this way. So if we look at it from behind, it's going to have a gravity acting down on it, a normal force going this way. It's going to have its IR. That means I theta would be into the page, and then K would be going up. I know this looks kind of ugly, but the Z axis would be going up. So that means angular acceleration is in the into the page, sort of thing. Okay, cool. Now, acceleration is this R alpha R plus 2 dr dt omega plus R. Oh wait, this is R omega. My bad. Plus R alpha. R omega squared. Jeez. Okay, and then we have, now we just kind of fill this in. So A is going to be, we know dt is alpha, so we know alpha c1t. We know that the second derivative position, this is alpha times h sine theta plus omega squared, which is 1/2 c1t squared times h cosine theta. And that's minus r, which is 2h minus h cosine theta times omega squared, which is 1/2 c1t squared. Yeah. Okay. Cool. That's the radial component of acceleration, plus 2 times dr dt, which we know is omega, which is c1, or 1/2 c1t squared. H sine theta, and then times omega. Okay, so another omega. So I'm just going to actually square this then. Right, that counts. It's 2 dr dt, which dr dt has an omega, times an omega there. Okay, cool. So that's just going to be 2 omegas together, so squared. Plus r, which we know is 2h minus h cosine theta, times alpha, which is c1t. All right, and that should be the answer there. So, acceleration and angular momentum. And if we really wanted to we could also express theta as 1/6 C1t cubed and plug that in as well. Okay, cool. So that's the answer for question 2. I'll just block those real quick. I'm not going to write them again. I'm just going to circle them, actually. Okay, cool. Next question. Okay, so a vertical axle is free to rotate. A massless horizontal rod is of length s, so that's our radius, is attached at its center to the axle as shown. There are 2 small objects attached to the rod. One of the objects has mass m1 and is fixed at the end of the rod. The other has mass m1 and is fixed at the other end of the rod. Okay, so they both have them. The axle is given an angular velocity of omega naught, and at time defined to be t equals 0, 2 small objects, each having mass m2, are dropped from a height h so that they hit and stick on the rod at the point shown. What will be the angular velocity of the rotating system after the objects hit the rod? Okay, so this is conservation of angular momentum because, again, it says free to rotate. So that means the torque, the external torque is 0. So we can use conservation of angular momentum. And so the way we're going to do that, and make sure my iPad doesn't die. The way we're going to do that is, again, we have L1, L initial equals L final. And again, we have L equals R cross P, which equals MR V naught, or V theta equals MR squared omega, both the K direction. So, the rod initially has angular velocity omega naught. Okay, so on the left, for L initial, we're going to have that we have these 2 masses, so I'm just going to say 2m1 for the mass times a massless horizontal rod of length s is attached to the center. Okay, so that means that this whole thing is s over 2. So s over 2 squared. I think that works. Yeah. Times omega naught. And then L final is going to have the 2 masses, so 2m2 times s to the under over 4 to the second power times omega plus 2m1 times the new angular momentum that we're solving for. So we can write 2m1 s squared over 4, 2m2 s squared over 16 plus 2m1 s squared over 4 times omega naught equals omega. We cancel out all these 2's and all these s squares. So we end up having m1 over 4, m2 over 16 plus m1 over 4. Which you can even simplify further to just m1 over m2 over 4 plus m1 times omega naught. I'll forget that. Okay. And then we're probably going to want the direction for this as well. Okay, so if we're looking at one of the masses on the rod, say this right one here, looks like it's spinning in the already spinning counterclockwise if we look down from it. So let's say this we're looking down. This is the top. Probably should have done this first, but I forgot to. But IR would be out. I theta would be, no Lord, It's doing that thing it was doing last video. Hold on a second. Just save it real quick. Maybe it won't do it anymore. Oh, it's going to do it. Okay. My bad. Okay, let's just relax. Okay, so IR is going to be, I theta is going to be in that direction. And then K is going to be out towards us. Okay, so that means the momentum would be in the counterclockwise direction, so it would be positive. Okay. Oh, writing in red all of a sudden. So counterclockwise. Just write that counterclockwise. All right, that's question 2. Okay. Question 4. A block of mass M is suspended by a massless, unstretchable rope from the pulley system shown. The pulleys rotate freely about the fixed horizontal axles. The rope moves around the pulleys without slipping. And so pulley 1 has a moment of inertia about its center of I1 and a radius of R1. Pulley 2 has a moment of inertia about the center of I2 and a radius of R2. If a constant force of magnitude P is applied to the rope as shown, what will be the acceleration of the block? Okay, so, yeah, this is a pretty good question. Okay, so let's do our free body diagrams. So for the mass M, it's going to have a tension force, tension 1 we'll call it, and it's going to have gravity acting down. And so we'll go ahead and just say that it's moving in the positive y direction there. Okay, cool. And we'll go ahead and define that it moves this amount S up. Then our first pulley has radius R. It has tension 2 acting on it there. And then it has tension 1 pulling on it in this direction. Okay. And then it has a normal force kind of diagonal out there to kind of balance off these two forces. Let me put these arrows here. And then just a little reminder, this is the positive X direction for this this pulley, and it's, since P is pulling up on the second one, they're all rotating this direction here, so like this. So yeah, that's important for later. And then we have our third pulley, which has a radius R1 and it has a radius R2, and it has P acting up on it here, and it has tension 2 pulling on it in this direction, and then it's going to have a normal force kind of to balance it out like this. Okay, so and then of course it's moving in this direction. Well, it's moving in this direction, some amount S, and this pulley's moving in this direction with some amount S. Right, and so this direction, though, is going to be the positive X direction for this pulley, because counterclockwise is the positive direction for these. Okay, so pulley 2 is moving in the counterclockwise direction, pulley 1's moving in the clockwise rotation, clockwise, because it's moving some direction S to the right, and pulley 2 is moving some direction S, pulley 1 is moving in is moving some distance S, or rotating some distance S in the clockwise direction, and pulley 2 is moving some distance S, or rotating some distance S in the counterclockwise direction. So Pulley 2 is going with the positive x direction, and pulley 1 is going against the positive x direction. Okay. So we got to set up our forces here. Let's see. So we got T1. We got T1 minus mass times gravity, which equals M, or capital M, A, Y for that. And then pulley 1 is going to have, let's see, tension 1 is pulling it in the counterclockwise direction, so it's going to be positive. So R times T1 minus, and since tension 2 is pulling it in the clockwise direction, it's going to be R1 times T2, and that's going to be equal to I alpha. I1 alpha, because we have a moment of inertia for the first pulley is I sub 1. Pulley 2 is going to have P times, or R1 times P, or R2 times P, sorry. R2 times P. And since P is pulling it in the clockwise direction, or making it rotate in the clockwise direction, or at least making it want to rotate in the clockwise direction, or counterclockwise direction, it's going to be positive. And then since tension force 2 is pulling it, or wanting to make it rotate in the clockwise rotation, it's going to be negative. So we have R2 times T2. And that's going to be equal to moment of inertia sub 2 times alpha. Okay. So we got to get these, we are solving for the acceleration of the block, right? So for pulley 1, we have that acceleration equals R alpha, right? R sub 1 times alpha. But since pulley 1 is rotating in the clockwise direction, it's going to be negative. And I should write over here that we're going to just define AI as A for that. And then for pulley 2, we have that it is rotating in the counterclockwise direction, so it's going to be equal to R, capital R sub 2 times alpha. Well, that's how we can relate angular acceleration to acceleration in this regard. And so we can go ahead and replace alpha with the expression we just created, equals times, so it means alpha is going to equal acceleration. Okay, so it's going to be negative A R1. Okay, and then for pulley 2, I'll just draw a line here. We're going to have R2 P minus R2 times T2. That's going to be alpha 2 times A over R sub 2. Because alpha is going to equal, there we go. And then we can go ahead, you go a step further and divide the R1s over, and actually put the negative from here, put the negative over here to make T1 positive. That way we can cancel out the T1 from this when we add all these together. So then we're going to have I1 times A over R1 squared, because we divided R1 over to the right-hand side. And then the same thing over here. We have P minus T2 equals moment of inertia sub 2 times A over R sub 2 squared. Okay, now we can add all these together because they all have they're all expressed in terms of A. Expressions that equal something in terms of A. So we're going to go ahead and just add equation 1, equation 2, and equation 3 together. One second. Sorry about that. Okay, so T1 minus mg plus negative T1 plus T2 plus P minus T2. Okay, and that's going to equal capital M times A plus inertia 1 times A over R1 squared plus inertia 2 times A over A2 squared. Okay, and so we can automatically see T1, the T1s are going to, the tension forces are going to cancel out. You kind of set up the free body diagrams right whenever those cancel. It's something you kind of just look for there. And so we're going to be left with P minus capital M G, which is going to be equal to M A plus I1. I'm actually going to factor out A right here. So A is going to come out, so we're going to have capital M plus inertia 1 over R1 squared plus inertia 2 over R2 squared. Yep, okay. And then, whoa, what is happening? Okay, then we have that acceleration is going to end up equaling P minus mg over m plus the inertias divided by the radius. Okay, cool. There we go. We have found the answer. Hooray. Yep, okay. And this is in the y direction, of course. I guess you could just put that back if you wanted to. But yeah, okay. So, essentially just for these types of questions with the pulleys, the thing you just got to try and be conscious of is what direction the pulleys are rotating in, and what the signs would be for the tension forces or for the torque, because these are the torques, right? And so a torque in the counterclockwise direction is positive, and a torque being applied in the clockwise direction or rotating something in the clockwise direction is going to be negative, right? So you just kind of have to think which direction is the pulley rotating in terms of this x axis you could write down. And then this question, I feel like I didn't explain it as best as I possibly could have, but essentially all we're doing here, and this is the angular momentum question, is we're thinking about, okay, so there's two masses of equal mass on the end of this rod that has a length s of like s, so that they're both equidistant from the center, or the center of the rod, which it would be s over 2 because it's half the rod's distance from this base. And so using this equation for angular momentum, this is what and since they're the only two masses on this rod at the time, and it already has an angular acceleration, or angular velocity of omega naught, this is going to be the angular momentum of the system initially. And then when these two masses are dropped on the rod at a distance s over 4 from the center, since they're the same amount, you can add them together. So it's just 2 times mass sub 2 times their radius or distance from the center of the rod squared times the new angular acceleration angular velocity, that we're solving for. And then to that you add pretty much the same thing from the initial, but now the angular velocity is changed. And so here we are with that, right? and then we're just solving for this with that one. And then you kind of do some cancellations, and then you end up getting this new value for the velocity. And then this question's, just the trick with this one is the fact that the radius isn't constant, and it's expressed in terms of theta, and so the derivatives are a little weird to take, but really all you got to think about is, okay, so we're given an r value here expressed in terms of theta, and so we need to take derivatives of that, but obviously we wouldn't be taking derivatives with respect to t like we usually would, because that would have made this whole thing 0, right? But so we kind of want to manipulate the derivative itself to be able to take a derivative with respect to theta, and so we get this kind of like equivalency to dr dt, because this is r, right, and it's being multiplied by d theta. So that would be dr d theta times d theta dt. The d thetas in the numerator and denominator would cancel out, leaving you just with dr dt like we originally wanted. And so that's how we get that, and that's how you end up with the extra omega term, right? And then we want to take a second derivative of that, of the radius, or the derivative of this, basically just taking another time derivative, which we can do this time. We just use the product rule, and so since h is a constant and omega is an unknown variable, we take the derivative of omega. But we also know omega is in terms of t, so we can take a time derivative of that. And so we take a time derivative of omega times h sine theta, because product rule is, the derivative of the first times the derivative of the second, plus the derivative of the second times the first. And so we had, the derivative of omega times h sine theta plus omega times the derivative of sine. But again, because sine is not expressed in terms of t, it's in terms of theta, we have to take a derivative with respect to theta. And so d theta dt times d theta is a way of doing that. And so we end up with this extra omega term again when we end up taking that derivative. So just kind of remember, you're going to end up with an extra omega term at the end of the day with some of these questions that have a radius in terms of theta, right? And so just that's the tricky part about these types of questions. But as long as you just remember, like, okay, I got to cancel out this thetas here. That's ultimately what you're going to be doing. So yeah, and then you just kind of plug it all back in. But yeah, that is Exam 3 2018. Good luck, guys, on the exam if you're taking it on Wednesday when I'm posting this. But yeah.